Today we're going to talk about torque and centrifugal force. It's a continuation of what we covered last week, which was on an introduction to sort of rotational dynamics, where we talked about moment of inertia and angular momentum. Today is a continuation of that, okay? And there are plenty of exercises at the end of this section for you to be working on. I hope you all had a chance to go through the lab type thing we did with the pulley, working out the moment of inertia. I know some of you, your tutorial was cancelled because Neil was away. I apologise about that. So, today we're going to talk about torque and centrifugal force. Most of it's on torque. We've got a small section at the end on centrifugal force. So, moments and torque. Okay, you covered quite a lot of moment stuff back in stress. This is not dissimilar, okay, but slightly different. We talk about torque, Newton's second law for rotating bodies, and then we've got an example. We're going to talk about torque impulse, work done due to a torque, and power due to a torque. We'll then look at the equivalence between between linear and angular, okay, motion. There are plenty of equivalent things you can do, and once you know the equations for linear stuff, as long as you know what to change the terms to and for the angular equivalence, you can know the angular equations as well. Okay, it's all very similar. And then we'll cover a small section on centrifugal force, including an example. So, you've all seen something like this before. This is a moment. We have a force being applied a distance r away from a pivot point, and we know that the moment is the force times the distance, okay, measured in Newton meters. Very, very easy to understand. Okay, the moment can be calculated as force times radius, m equals Fr, and the radius is always the distance perpendicular from the line of action of the force to the pivot point. So that angle there, which I've got on the thing, is always going to be 90 degrees, okay? If the force is being applied up here to a pivot arm, but that force is in line with this one, then it's the perpendicular distance, not the direct distance, okay? That's moment. You've all covered that before. You should have done last semester in stress. Now, last week we covered angular momentum, okay? We know that angular momentum relative to an arbitrary point q is rq, which is the position vector r from point q to the whatever it is that's moving, times by its momentum, p, okay? Rq cross p is the angular momentum. Now, if we take the derivative of that with respect to time, okay? Taking derivative with respect to time, we have to use differentiation by parts. Okay, so we have the derivative of the position vector with respect to time, cross p, plus rq cross the derivative of momentum with respect to time. Now, what's the derivative of displacement with respect to time? Velocity, okay? And the velocity of whatever it is that's moving will be in the same direction as vector p, okay? So they're in the same direction, because obviously p is a function of velocity as well. And so we've got v cross mv, okay? Now obviously they're going to be in the same direction. So what's two vectors cross two vectors that are in the same direction? What's that value? Well, if you think about the equation for the magnitude of a cross product, okay? Do you remember it was the magnitude of r, or the magnitude of dr over dt, times by the magnitude of the second term, okay, times by the sine of the angle between them. Now what's the sine of 0? 0, okay? So this term here, drq over dt cross p, is 0. We can disregard it, okay? Because the velocity of that particle and the momentum of that particle are always going to be in the same direction. So that term just drops out. And so we have the derivative of angular momentum is going to just be rq cross the derivative of momentum divided by time. Okay. And what's the derivative of momentum divided by time? Back when we did this, well, I think you did it with Neil, lecture 5, okay, we said that the derivative of momentum divided by time is the force, yeah? Do you remember that? You looked at the body of particles, and if there's no external forces, then there's no change in momentum, okay? Well, it's the same thing. dp over dt, we know, is the force, okay? dp over dt is the force. And so we can say, so as I said, v and p are in the same direction, and so that value equals 0. dp over dt is the force, and so the derivative of angular momentum is rq cross f, okay? rq cross f, which we know as torque, okay? Torque is rq cross f. Now remember, f cross r does not equal r cross f. So you've got to make sure you get them the right way around, okay? Otherwise you'll get the wrong answer. And remember, we always use right-handed coordinate system where I cross j equals k, okay? If you do it the other way around, you'll get a negative value for the direction, which is not what you're looking for, okay? You get the wrong value for your direction. So that's torque relative to point Q, okay? R cross F. Now, let's take an example. We've got the Earth rotating around the Sun. Okay, so here's the Sun at point C. That should really be RC, not RQ. Apologies, okay? And that M there is the Earth, okay? So this is the Earth rotating around the Sun, comme ça, okay? And it's rotating with a linear tangential velocity v, okay? What's the torque being created? Well, the torque is going to be RC, okay? Like I said, that should be C, not Q, cross F. Now, what's the angle between RC and F? No, it's not 0. RC is in this direction, F is in this direction. What's the angle between them? 180, yeah? Okay, what's the sine of 180? Basic trick, guys. Sine of 180. No, 0, exactly. So, the Earth rotating around the Sun, okay, there's no torque being applied to the Earth, okay? Because the only force is obviously the gravitational force between the Earth and the Sun, okay, centripetal acceleration or centripetal force, okay, and the gravitational force due to their masses. And that's rotating around the Sun, but there's no torque being applied, okay? Although it's rotating, there is no torque, because the force that's being applied is directly opposite to the position vector, okay? And because those angles are 180 degrees apart, we know that sine of 180 is 0, and we know that a cross product, the sine of the angle between them is part of the magnitude of the cross product. And it happens that because we've got sine of 180, that value is 0, so the magnitude of the torque being applied of the Earth rotating around the Sun is 0. What about if we've got a force being applied tangentially to a disk? Okay, so here we've got a different situation. We've got a disk, radius r, rotating at omega, radial speed, and there's a force being applied to that disk. Okay. Well, the magnitude of the cross product, okay, we're going to have, obviously it's going to be, the torque is going to be r, okay, cross F. And the angle between R and F is what? 90 degrees. And what's the sine of 90? 1. And so essentially it's a scalar multiplication of R and F. So T equals FR, which is exactly the same as the moment. Yeah? So that's where that moment thing comes from. F times R. Okay, well it's because we're perpendicular, okay, the force being applied tangentially to the disk is going to be a distance r away from the centre of that rotation. Okay, so the torque being applied is going to be force times the radius. Okay. Now, as I said in the lecture to do with Racing Academy, okay, during that activity week, the engines produce torque, not power. Okay. Well, this is exactly that situation, because essentially and in your book you've got a picture. There's a crankshaft, the piston, and there'll be a force being applied by the combustion of the fuel. Okay, and that applies a force tangential to the crankshaft. And so that's where that FR comes from, R being the radius of the crankshaft, or the big end from the centre of the crankshaft, and force is obviously the force being applied by the combustion of the fuel. And that's what causes the rotation of the engine. Okay, so as I said, engines create torque, not power. Power is merely a function of the torque that it creates. We'll talk about that in a second. So the direction of the torque vector follows the right-hand rule. So here we've got an anti-clockwise direction. Okay, anti-clockwise, there's our A, there's the B. Moves anti-clockwise, so the torque is coming out of the screen in this situation. Okay, anti-clockwise is out of the screen, clockwise is into the screen. Here we've got anti-clockwise direction, so it's out of the screen. We also know that angular momentum for a disk is I omega. Okay, remember I talked about that last week. There was the computer hardware company called I omega. They obviously took their name from rotational or angular momentum. And if we, as we said, if we take the derivative of angular momentum, you get the torque. Okay, well, what happens to I omega when you take the derivative of that with respect to time? Well, you get I d omega over dt, and obviously the first derivative of omega, which is the angular velocity, is the angular acceleration. So you have the torque is I alpha. Okay, now we covered this in the third lecture when we were doing free body diagrams. Remember I said the sum of the moments is going to be I times alpha. Well, that's this. Okay, it's exactly this. That's the same thing, where alpha is the angular acceleration. Okay, so you've already had a chance to use that in your work, but this time it's going to be more apparent. Okay, and this is the angular equivalent of Newton's second law. Okay, F equals NA. We all know that. We know that very well. Okay, well the same thing for angular motion is torque equals I alpha. And so we can see that force and torque are equivalent. The mass and the moment of inertia are equivalent, and A and alpha are equivalent. And so we can make some comparisons between angular and linear equivalent. So a torque is angular equivalent of a force, the moment of inertia is the angular equivalent to a mass, and the angular acceleration is the angular equivalent to linear acceleration. Okay, now we'll cover a few more of these in a bit. But first off, we've got an example. This is on page 116. Okay, I've got my... I'm afraid I haven't printed out the page, so you'll have to... So this is 8.1.4. 8.1.4. Example. Can you all read that? Okay, and what we've been given is a disk. Again, it should be a circle. It's not, but there we go. Okay, and we've got a force being applied here. That's F1. We've got a force being applied here. That's F2. I'm assuming right-handed coordinate systems. So that's I, that's J, that's K. Okay, and we know the radius of this disk. That's 0.6 meters. Okay, we've got a mass that's been given in the question, 0.15 kilograms. And it says, determine the instantaneous linear acceleration of the puck and the angular acceleration of the puck, stating any assumptions. Now, there's a couple of bits of information that I forgot to give you in the question, okay? And that is the values for F1 and F2. Okay, F1, this is in the positive J direction, and that's 5 newtons, okay? So 5J newtons. And F2 is in the negative J direction, that's going to be negative 2J newtons. Okay, so those are the bits of information that we need. And it says we've got to work out the linear acceleration of the puck. So by applying those forces, okay, the thing's going to move. Okay, and we've got to work out the angular acceleration of the puck. And so linear acceleration of the puck, well, we know that the sum of all the forces is mass times acceleration. Okay, and so that's going to be F1 times by J plus F2 times by J. So we substitute those values in, 5J minus 2J, so that equals 3J. And so A is going to be 3J divided by the mass, 0.15 kilograms. So that comes out to be 20 J meters per second. Okay? It's going to move upwards, which makes sense. You've got a bigger force at F1 and a smaller force at F2. It's going to move in that direction, linearly in the... Okay, now, what about angular? So that's the linear acceleration. Okay, angular acceleration, well, we first need to work out what the moment of inertia is. Moment of inertia, that's I, equals 1/2 times by the mass times by the radius squared. Okay, well, the radius is 0.3, so we've got 1/2 times by 0.15 times by 0.3 squared. That comes out to be 6.75 times 10 to the minus 3 kilograms meter squared. So there's our moment of inertia. And we know that the sum of all the moments, okay, is torque, which we know is I alpha. Okay, and we also know that torque equals R1 cross F1 plus R2 cross F2. Okay, remember they're vectors, they're cross products. Okay, we've done this. Obviously, we can tell that R and F are 90 degrees apart, but we've done it cross products anyway. Okay, and so we can say that R we know is 0.3 times I. Okay, that's the distance. Cross F1, which we know is 5J. Okay, again, R2 is going to be 0.3 times I cross minus 2J. Okay, so this is cross products. What's I cross J in the right-handed coordinate system? I cross J is what? K. Okay, so we know that the vectors on these results are going to be K. And so 0.3 times 5, well, that's going to be 3. No, it's not. It's going to be minus 1.5, okay, times by K. Why is it minus 1.5? And we've got minus 0.6 K equals minus 2.1 K Newton meters. So that's the torque. And so we take alpha, we divide that torque, minus 2.1 K divided by 6.75 times 10 to the minus 3. Yeah, you're right, that should be plus, shouldn't it? Because it's 0.3 times by 5. Yes, that should be plus. Sorry. So that's plus, minus, so that's 0.9 K. Okay, so alpha is going to be 0.9 K divided by 6.75 times 10 to the minus 3. Which, where's my trusty calculator gone? There it is. So we have 0.9 divided by 6, or 0.00675. So we get 133 K radians per second squared. Okay? Yeah, so we have a clockwise rotation. K is into the board. No, sorry. Okay, it's fine. We'll leave it as it is. Yeah, okay. So, Okay, so we have that example. We now talk about torque, impulse, work and power. Okay. Well, if you remember from, I think it was the week before last. No. In fact, this was again lecture 5 with Neil's stuff. Force impulse is the differential of force with respect to time, or so the integral of force with respect to time between T1 and T2. Okay, well we can say, by definition, for a varying torque that we have exactly the same situation. All we're doing is replacing F with T, okay, and you have a torque impulse. And so for a constant torque, it's basically the torque times the time of that application of that torque, okay, which both have units of Newton meter seconds. Okay, so that's torque impulse. You also remember that the torque is I alpha. Okay, if we replace alpha with d omega over dt, we get t times dt equals I times d omega. And so we can integrate both those sides, and we end up getting the torque impulse is going to be the change in angular momentum. Okay, and that's equivalent to the linear value. We had the force impulse was the change in the force in the linear momentum. Okay, P1, P2 minus P1. We've got the same thing here, where h is the angular momentum. Okay, in section 6, we discussed work done by a force, which was W equals integral of A to B of the force times the distance. Okay, well, work done by a torque is exactly the same, except for this time, instead of x for displacement, we've got theta. Okay, that's the angular displacement, and it's the torque being applied across that angle. And so, for a constant torque, we've got torque times by the change in theta. Okay, and again, the units are joules, which is the same as linear motion. So that's the work done by a torque. Again, applying Newton's second law, we know that torque equals I alpha. So replacing alpha with d omega over dt, we've got I d omega over dt. And we know that d theta equals omega dt. Okay, so applying those substitutions, okay, we've got the integral of torque times dt. Okay, well we replace that torque by dt. Sorry, d alpha, d theta, I mean. Torque times d theta, okay, we replace those with the things we substituted up there. And we end up getting an equation where the work done is also equal to the change in kinetic energy, rotational kinetic energy. You'll remember that 1/2 I omega squared is the kinetic energy associated with something that's spinning. Okay, so the angular kinetic energy is the work done. Now, power, you'll remember, is work done over the time taken. Okay, and for linear motion, we said the power is force times velocity. Okay, well, for torque, the equivalent can be used. Instead of force, we use torque. Instead of velocity, we use omega. Okay, so power is torque times omega, which is where the power from an internal combustion engine comes from. You take the torque value at a certain speed, okay, you multiply by the speed, and you get the power. Okay, which is why, if you remember, the answer to the first question in your Racing Academy worksheet was what's the best characteristic for an engine, and the idea for that was essentially a rectangle, a high torque over a wide range of speeds, because that will give you the maximum power, because you've got speed as the end product. Okay. So we can draw some equivalence between linear and angular motion. Okay. We said the resistance to acceleration. Well, for linear motion, that's the mass. For angular motion, that's the moment of inertia. Okay. Acceleration, the force that produces acceleration. Well, for linear motion, that's the force. For angular moment, that's the moment of force or a torque. Momentum is mv or I omega. Newton's second law. Well, Newton's second law is the derivative of momentum, which is the same. Or, that should be t, by the way. Newton's second law, we've got force equals mass times acceleration, or the torque equals I alpha, and the kinetic energy, 1/2 mv squared, 1/2 I omega squared. Work for constant, force for torque is going to be the change in kinetic energy in both cases. For varying torque or force, okay, we've got again the change in kinetic energy. Impulse, Ft or Tt. An impulse for varying force or torque is going to be the change in momentum in both cases. So the real key here is essentially if you know one side of this table, okay, we know all the linear stuff, you also know all the angular stuff. It's exactly the same. For force, you put in the torque. For x, you put in theta. For a, you put in alpha. For v, you put in omega. Okay? And time is the same, irrespective. Okay? So, we've got another example. And this is on page 120 of your book. Okay, so this is 8.3.1. Okay, it says a flywheel in the form of a disc in 1 meter diameter and mass 100 kilograms is accelerated from rest by a torque of 1 Newton meters. How long and how many revolutions does it take for the flywheel to reach a speed of 60 RPM? Okay, so omega 1, we know that 60 RPM, that's going to be 60 times by 2 pi. Okay, which is 6.28 radians per second. Because in one revolution there's 2 pi radians, okay? That's 60 RPM, obviously that's divided by 60 because there's 60 seconds in a minute, okay? So obviously they cancel, we end up getting 2 pi, which is 6.28. We know that the radius of gyration, okay, is going to be, if you remember for a disk, we've got I equals 1/2 mr squared, okay? And that equals m times kg squared, okay? So that value there equals kg squared equals 1/2 times by r squared. 1/2 r squared. So that's going to be 1/2 times by, we've got a radius of 1, sorry, a radius of a d of 1, so a radius of that, so we get that, and that equals 0.125 meters squared. So I equals m kg squared, so that's 100 times by 0.125, which equals 12.5 kilograms meters squared. Okay, so there's our value for moment of inertia. So we know that torque equals I alpha. So alpha equals the torque divided by I. Now the torque is 1, I is 12.5. So alpha equals 0.08 radians per second squared. Okay, we can determine that. And we know the torque impulse, torque delta T, equals I omega. Okay, so delta T, which is what we're trying to find, the time it takes, is going to be I omega divided by T. So we're going to have I omega, well there's omega, so I is 12.5, have 6.28 divided by omega, sorry, T, which is 1. And so we have 78.5 seconds. So there's the answer to the first bit, 78.5 seconds. And now we know we're applying a constant torque, and so we can assume that the acceleration is constant because the relationship is I alpha, And so we can use the Suvat equations, but in angular form. And we know that Suvat equations is omega naught t plus 1/2 alpha t squared. That's the same as x equals ut plus 1/2 at squared, but this is an angular form. Now what's the initial velocity? 0. Accelerates from rest, so that drops out. And so we have 1/2 times by alpha, which we calculated up here, 0.08, times by t squared, 78.5 squared. And so alpha comes out to be 246.49 radians. And to get that in revolutions, you divide by 2 pi and you get 79.23 turns. Okay? So those are the answers. And we know that it's 2 pi radians in 1 revolution. And so if we divide 249.49 divided by 2 pi, we get 39.23 turns, revolutions. Okay, so that was talk. We've now got the last few slides. Okay, centripetal force and centrifugal force. Okay, we know that when a body is rotating, okay, there is an acceleration from the particle, okay, to the centre of that circle. Okay, and that we know is centripetal acceleration. If you are unfamiliar with it, it's in the revision notes which are on Blackboard. Okay. There's an acceleration force, acceleration being felt by the particle that's rotating around to the centre of the circle. And that's due, we know that if you have a change in velocity, okay, you get an acceleration. Well, here the velocity is changing, okay, it's not changing in magnitude, but it's just changing in direction. And so there must be a corresponding acceleration, and that acceleration is an acceleration towards the centre of the circle. Now the value for that acceleration we can write as omega squared r. And knowing that omega is equal to v divided by r, then you can also replace omega squared r with v squared upon r. Okay? And so centripetal force, okay, is obviously that mass times that acceleration, where a is v squared upon r, or omega squared r. So that's the centripetal force. Now, from Newton's third law, for every force there's an equal and opposite force, okay? And so if there's a force towards the centre of the circle, there must be an equal and opposite force away from the centre of the circle, okay? And that we call as the centrifugal force. And that's the force you feel when you're going around a corner in the car, okay? The car is applying a centrifugal force to your side, okay? Centripetal force to your side, keeping you going round that corner, okay? And you're applying an equal but opposite force to the car, okay? Which you can feel as the side of the seat, okay? And that is the centrifugal force. So they're equal and opposite to each other. And so we can say that the centrifugal force, okay, is simply the centripetal force, but negative. So it's mass times v squared upon r, obviously minus omega squared r. Okay, so it's very easy stuff. If you know centripetal force, you can know the centrifugal force. And we apply this in all sorts of different ways. I was particularly close to it during my days as a research officer because I was looking at a tilting vehicle. Okay, now tilting vehicles, like motorcycles, they're essentially what they're trying to do is balance the centripetal or centrifugal force or centripetal reaction force with the mass, which is why it leans into a corner. And so, let's do that example. This is on page 122. We've got a motorcycle, rides on a level, camberless road, and executes a turn with a radius of 75 metres. Says the coefficient of friction between the road and the tyre is 0.64, okay? So he's obviously got a very poor tyre or a very smooth road. And part A says calculate the angle theta that the motorcyclist makes with the vertical when travelling at 15 metres per second. So we've got 8.4.1 part A. So what I'm going to do is I'm going to draw a picture of the motorcycle. Okay, so here's the ground. Okay, and here's the motorcycle, simply a centre of mass. Okay, and we're not going to bother with the dynamics of the motorcycle. Okay, we've got mg here. Okay, this angle I'm going to call theta. Okay, and we know that there is going to be a friction force in this direction, a normal force in this direction, N, FF, and we know that there is a centripetal force or acceleration in this direction, which I'm going to call m v squared upon r. Okay? And so if we do the sum of the moments, okay, about the pivot point, my axes look like this. I've got mgr, so that's the positive, okay, so that equals 0 because we don't want it to roll. We've got m, g, r. Now obviously this distance here, that distance there, that's going to be r sine theta. So that's going to be r sine theta minus mv squared upon r. Okay, that's that, and that's going to be applied over this distance, which we know is r cos theta. Okay, they cancel. And so we can say that mg r sine theta equals m v squared cos theta. The m's cancel. We end up with, if we divide by cosine on both sides, we have sine over cosine, which equals tangent of theta. And that's going to be v squared upon rg. And so we know that theta is going to be the inverse tangent of v squared upon rg. And so for this case, we've got r is 75, g obviously is 9.81, and v we've been given is 15 metres per second. And so theta equals the inverse tangent of 15 squared divided by 75 times by 9.81, and that comes out to be 0.297 radians, which equals 17 degrees. So that angle, theta, is 17 degrees. So the motorcyclist is going around the corner at 15 metres per second. Radius of 75, we know the angle that it makes with the ground is 17 degrees to balance out those forces. Because the idea of riding a bike is you don't want any moment affecting your angle. Okay, so that moment is 0. And so we just apply moments about that pivot point, the contact patch between the road and the motorcycle, and you end up getting that angle. Now part B, it asks, calculate the maximum speed at which the motorcyclist may take the bend if sliding is not to occur. Okay, well, so we've got this friction force. Okay, we know mu is 0.64. And we know the friction force is going to be mu times by the normal force. Okay, so if we do the sum of the forces in the x direction, that's mass times acceleration in the x direction, which we know is 0 because it's not accelerating in the x direction. And that's going to be the friction force, FF, minus the centripetal reaction force. Or Okay. And so that equals mu n minus mv squared upon r. And so we can say mu n equals mv squared upon r. In the y direction, the sum of the forces in the y direction equals mass times acceleration in the y direction, which also equals 0. And so we've got mg minus mg plus n. And so we can say that n equals mg. And so by plugging that into this equation, let's bring that down here. We've got mu mg equals mv squared upon r. M's cancel. And so v equals the square root of mu g upon r. No, mu g times r. Apologies. Mu g times r, so that's going to be the square root of 0.64 times by 9.81 times by 75. And that comes out to be 21.7 metres per second. And what angle does this make with the road, part C? Well, we can just use that equation. Theta equals the inverse tangent of v squared upon r times g. So that's inverse tangent of 21.7 squared divided by 75 times by 9.81. And that comes out to be 32.62 degrees. So there's your answers to those parts questions. Move it up. Is that good? Okay, so in summary, moment applied by a force is the force times the distance. We all know that. Torque, if you're dealing in vectors, is r cross f, not f cross r. R cross f, which when you take the first derivative of momentum, you get the same thing. You get torque. And if the force is tangential, the cross product becomes just a simple multiplication. Force times distance, okay, which is what we have for moments as well, okay. Newton's second law, F equals ma. Well, here we're dealing with torque, so it's torque equals I alpha. The torque impulse is torque times the change in time. For a constant torque, that's T delta T, which we know is the change in angular momentum, H. The work done, that's torque times the change in displacement. For a constant force, a constant torque, which we know is the change in kinetic energy, rotational kinetic energy for a disk. Power, we know, is torque times the angular velocity. And we know there are some angular and linear equivalents. These are the same tables that you've got in the book. So we've got resistance to acceleration, what produces acceleration, momentum, Newton's second law, kinetic energy, and then here we've got work, impulse, for both a constant force or a torque and an impulse for a constant force or torque. And we know that centrifugal force is simply minus the centripetal force, which is the mass multiplied by the centripetal acceleration, which for things going round a corner is v squared upon r, or omega squared times r. Right, before you all head off, I've got a little thing to show you. I've got here a piece of plastic, okay, simple piece of plastic. And what I'm going to do is I'm going to apply a torque to it, okay. If I apply a force to it, obviously it's going to move this way, but I'm going to apply a torque to it, so I'm going to apply that force. I apply a torque to it in this direction. Do you want me to do that again? Made in China. It is made in China. Something for you to think about during the next week.